So hello, everyone. Excited to be here today talking about our journey in Thousandize with Apache Druid. We were able to reduce the latency of our dashboards by an order of magnitude. There were definitely a lot of lessons learned along the way, and I hope to share some of that today. So a little bit about me. I'm a lead software engineer in Thousandize, been with the company for a little bit over 3 years now. And I've been leading the efforts to adopt Druid from the initial POC to the production deployments. And so just to provide a map of what I'll be talking about in this talk, I'll first start with a little intro on Thousandize and what is Apache Druid exactly powering Thousandize. And then I will focus on our production clusters. This is going to be the main focus of my presentation, talking about how we deploy our clusters, what they look like, and how we use Kafka and how we partner with Imply to deploy them. I will also be speaking about how we optimize our queries, or how we think about how the data is laid out on disk to optimize our queries. And then I'll also speak about some of the challenges when you're ingesting real-time data in Druid. All right, so let's get started. What is Thousandize? If I had to describe Thousandize in just a single sentence, it would be that we're a cloud intelligence company. We enable our customers to deliver superior digital experience. That's how we like to put it. There are a lot of stats about our company in this slide. We were founded in 2010. We were acquired by Cisco 10 years later in 2020. And we have some of the largest Fortune 500 companies as our customers. And if you think about digital experience, it used to be that companies controlled everything with respect to their networks. There was a data center where all applications were deployed. Branch offices had direct connections to these data centers, and this was the complete view. However, the world has dramatically changed. Right now, companies depend on external vendors, on ISPs, on CDNs, on DNS. Your applications will likely be deployed on multiple clouds. And the only common denominator here is that in order to access all of this, you depend on the internet. And, let's be honest, the internet is fragile. There's no SLA on the internet. So with Thousandize, you can see into every one of your networks, including the internet, like it is your own. And I think this picture right here depicts really well what we do. You can see the traffic from a particular customer to a vendor, and you can see that it navigates through the internet. And in this picture, you can see hop by hop how the traffic is flowing. So you can see that even though all these red dots that are in the internet and in the vendor may be causing issues in your application, but with traditional tools that were used when there was just a single data center, you couldn't really see what the root cause of these issues was. But with Thousandize, you can actually go and investigate into what the problem is. So you can imagine that in order to form this nice picture right here, there is a lot of data that needs to be collected. So in order to show this data to the users and how the performance of their networks how their networks have performed over some large period of time, you need a technology that is specifically designed to handle large amounts of data and responds to queries really, really quickly. And that's where Druid comes in. So what does Druid power in Thousandize? Well, it powers the dashboards. We have customer-facing dashboards that essentially are a collection of widgets. They're highly customizable, so our customers can drag and drop these widgets into dashboards, and they can configure them with many group bys, many filters, and visualize a lot of metrics. And you can think of it as a way for our customers to interact with their data, to ask questions to their data. So you, for example, may be grouping by your network performance by country, and you see a country that's in the red, so now you want to drill down into that country and see which sources within the country were the root cause of your problem. All these changes that you make to the widgets in order to visualize your data are queries to Druid, and you want these queries to be really, really fast. And that's what we call our fast access pattern. Now, to access this data, we also have what we call a slow access pattern, which is mainly used for scheduled reports or even internal teams within Thousandize that need to access the historical data, but don't necessarily need the fastest speed or the fastest queries. Therefore, we needed a system that would support very well these two use cases: a very fast one that is based on human clicking buttons and trying to interact with data, and a slow one that is mostly for scheduled reports and internal teams. So taking a step back, how did we power these dashboards before? Well, we had a solution that worked really well until a certain point. And the fundamental problem that it had is that we were essentially reusing an OLTP data store for OLAP queries. And to be quite frank, this doesn't really scale. It reaches a point where it doesn't scale. So we were having problems where our dashboards, and particularly when you were looking at historical data, they were just taking too long to load. And you can imagine that if you're trying to visualize your performance around 15 days and you're trying to drill down into, the different metrics and group bys and different things, you can't really wait 15 minutes for the next thing to load, right, when you modify your widget. So with Druid, we were able to reduce the performance quite a bit. And it's not only that we achieved great performance, it's that we achieved consistently good performance. And that's really what it was all about. But there's still a question: is Druid the only technology that is able to deliver something like this? Well, we really investigated a lot of technologies, and for us, Druid was the superior choice for our use case. Really, I'm only going to focus on these two main ones because they were the two main competitors. But if I had to summarize why we chose Druid, is because Druid is basically the best. It's a better ecosystem for handling large amounts of data. So when you are handling large amounts of data, one of the great characteristics about Druid is that it provides you a lot of flexibility with how that data is stored. You can essentially repartition your data very easily and out of band of the nodes that are actually running queries and ingesting data from Kafka. So the ability to reshape your data after it's been ingested, it was really important for us. And not only because you might, not know before you're running in production what the best optimal, partitioning system might be, but also because, access patterns change over time. Product management may come later and tell you, okay, now, you may have they may want to change your, support some new feature. And for that, you need a new partitioning system. And if you have a data store that doesn't allow that, you basically have to go back and say, well, we can't really do it. It's not feasible. But with Druid, you're able to say, sure, give me a couple of sprints. Then the other aspect is about I mentioned that we have two access patterns. And with Druid, you can essentially in the same hardware run different queries with different priorities, such that your high priority queries will actually kick out from CPU the low priority queries, thus always achieving fast performance on those subset of queries that you want it to be really fast, and slower performance on those that you don't really care that much. And this is within the same hardware. And yeah, the other things that were really useful for us is that with Druid, you have native integrations with Kafka and S3. So you can really ingest from these two sources just by changing a JSON spec. Where there is no service to maintain, to monitor, to set up alerts on, or custom pipelines to build. It's just changing a JSON spec. So for us, as I said, it was a better ecosystem for handling large amounts of data. All right, and now focusing on our production clusters and how we deploy them. Well, the very first thing I wanted to do is do a 30,000-foot view of what our architecture looks like. And you can see the main piece is Druid. We have ingestion to the left and queries to the right. So let's focus on each one of them. So ingestion, all our events really come from what we call thousand-eyes agents, which are constantly collecting metrics about the different networks. And we push those out to Kafka, we enrich them, transform them, and do different processings on them. And eventually, after they're denormalized, we ingest them in Druid. We also have a batch ingestion that I'll talk a little bit more about later. But yeah, in terms of data volume, we process about 1.5 billion events per day. We have about 10 terabytes in production, 10 terabytes of Druid compressed data. So really, our raw data is actually 20 to 30 times more if this was just JSON. And then we have about 35 data sources. And then let's look at the query side of things. We have between 5 to 20 requests per second, and we have sub-second latency for most of our queries, and our 98th percentile latency is about a second. We do have queries that take a little bit longer, but the majority of our queries are sub-second. All right, so let's focus on the main central piece, which is our Druid architecture. The way we deploy Druid is actually a multi-region base. So we have 3 regions, and we deploy 14 clusters in these regions. The reason we have that many is because, well, there's different environments that we deploy, staging, production, and also we have active regions and disaster recovery regions. So, why so many clusters? And really, it's not too cost effective to deploy a lot of Druid clusters. If you deploy a single Druid cluster, all your data is located in there. Druid, democratizes the resources much better, and you can, be more cost effective by just deploying less clusters. But for us, it was a matter of 3 things. First, we have a business requirement where we need to isolate the data for certain customers in a particular region. So in that case, you just have to have a cluster in that region and another cluster in another. But also for reducing operational risk. When you think about a dashboard, right? If a cluster goes down and you're holding all the data in that cluster, all your dashboards are gonna fail. But if you're able to partition your data by region, and within each region partition your product areas in different Druid clusters, so essentially having more smaller clusters, you can load partially your dashboard, right? Some widgets will load because the clusters are working and the others maybe not. So really, it's a matter of reducing the risk here and business continuity. All right, let's zoom into one of our clusters. This is what one of our typical clusters would look like. By the way, we deploy with Imply Manager, which provides a really nice UI to kind of deploy in AWS, and it abstracts away some of the most complex tasks when deploying a cluster. And yeah, we deploy 3 master servers always because this allows us to do rolling deployments. Our master servers, we deploy always with at least 8 vCPU because we run a lot of real-time ingestions and compaction. So we need to make sure that the active master node is always, able to keep up. Then on the query side, we deploy a minimum of 2 nodes. In case one goes down, we have another. And also we tend to keep a ratio of 1 query node per 10 to 15 historicals. Then on the data side, we deploy nodes that are storage optimized, so i3 in AWS type of nodes. And we always deploy in 2 tiers, where tier 1 essentially takes care of holding the data and responding to queries, and also runs Kafka ingestions. And then we have a tier 2 where we process batch ingestions out of band. And when I say out of band, I mean that you can schedule those Kafka ingestions, you can scale out tier 2 independently of tier 1, and you will never affect your queries or your real-time ingestion, which is the most important part of your cluster. All right, so this is what our cluster looks like. But if you're coming to Druid, you likely want to do one thing above all else, which is aggregating large amounts of data really quickly. So it's important to think about how are you going to optimize your queries. But to optimize your queries, you really have to first start thinking about how is your data layout looking. So really, when you're thinking about query optimization, query performance optimization, you need to be thinking about 2 things. How do I read less segments? And from the segments that I do read, how do I put my data together such that I have to access the segment less times? If you think about how a query works, right? A query is received by the broker, and then it's fanned out to the different historicals that hold the segments. So you want those subqueries to be the less number possible, so potentially just 1 in the best case, right? And the segment that you do access, you want all the rows that you're going to be accessing close together. And we're going to be talking in the next few slides about how to achieve that. So let's talk first about data layout. In our case, we have a multi-tenant system. So one of the first things you should do when you're thinking about how to improve your data layout is choosing wisely your first dimension, because your segment, that's going to determine the sorting of all the dimensions in your segment. So by choosing, customer ID, which is a dimension that you always filter by if you have a multi-tenant system as the first dimension, all your data for that customer is going to be grouped together. So remember that Druid accesses segments in sort of batches. So if your data is scattered across the segment, each batch that Druid reads, first it's going to have to read more batches. And each batch that it reads, there's only a small subset of relevant rows within each batch. Whereas if you group it together, Druid can do less accesses to the segment. And then each access you can read more rows that are relevant. So, well, this is, the first thing you should be thinking about. But this representation is actually a little bit simplistic, because if you see the time dimension, is all the values are exactly the same. We have the same timestamp in every single row. So even if you choose your dimension well, really not all your data is going to be located in one place of the segment. What's going to happen is this image on the left. For every different timestamp, you're going to have the data of your customer grouped together. So you're going to have groups scattered across your segment, which is still pretty good. In fact, we use this in production and it works really well. But there's, extreme optimization that you can do. And Gian Merlino actually has a really nice talk about this, where you can actually round the time dimension to exactly the same value for every row in your segment. And then, basically you remove it out of the picture for in terms of sorting. And now your primary sorting dimension becomes the first dimension that you chose, customer ID. What that means is that all your data within a segment is going to be in a single place within the segment for that particular customer. And, we tried this, and we achieved about a 50% improvement in performance and query latency. But, it also complicated our query layer quite a bit, because there's some things that once you do this optimization, you can't really use that come out of the box with Druid. Like, for instance, if you want to define a granularity in your queries to essentially bucket your data every, let's say, certain hour, you can't just use granularity anymore. You have to do custom things like rounding the time dimension to the hour and then grouping by it. So because it complicated our query layer and the performance boost was not that large for our use case, we actually just kept what I show here on the left. But it's something to think about if you really need that performance. All right, so now every segment that we have is more performant because we're grouping the data that we query together. But the next thing that we need to be thinking about is, I'm reading 4 segments. How do I make that such that I only read 1? And the answer to this right now would be secondary partitioning. Druid allows for multiple secondary partitionings. The partitionings in Druid are really dynamic hash or single dim, and you can choose between these 3. But we are using in production single dim, which basically does a range-based partitioning. So there's going to be a range of customer IDs that are stored in any given segment. And one caveat here is that you need to be very careful with your largest customers, because they're going to be basically in a single segment. And if they're large enough, they're going to make that segment super large. And that becomes problematic in a Druid cluster. So watch out for that, and you have to try different options. And this is when the flexibility that Druid provides is really nice to optimize for your use case and your access patterns. So yes, it's definitely something to investigate. The thing that I want to mention though is that Kafka ingestions, when you're ingesting in real time, you actually can't apply this secondary partitioning right away. The only way that I know of that you can actually do some sort of partitioning to improve the layout is doing it upstream. So you can essentially partition your Kafka topic based on customer ID. You have to be still careful about hotspots, but that's the only way to do it in Kafka. But then after it's ingesting the cluster, I would definitely recommend applying secondary partitioning. That way your broker, when it receives a query, it knows that it doesn't have to query every single segment. It can only just query that segment that holds data for your customer ID. The only requirement is that your query must have a filter on customer ID, which in a multi-tenant system, that's pretty much always the case. All right, so let's look at, how do you apply the secondary partition? Where in our case, we apply it thanks to auto compactions. And this is something that I would highly recommend anyone that is ingesting in real time to enable in your cluster. Auto compaction basically runs with some delay on the real-time ingestion. We run it about 2 days after the data was ingested, and essentially reads Druid segments and writes more compacted, more optimal segments back into Druid and replaces the ones that were there. So, with this, you can reduce the number of segments that you read. You can improve the data layout. You can remove you can do a lot of things. So highly recommended. You can also change the segment granularity. No, not the segment granularity, but the partitioning system, which is how we apply that secondary partitioning to our older data. And yeah, some tips and tricks in terms of, auto compaction. Late events are not your friends. Late events actually mess with compactions. When you receive a late event in Kafka, basically, if there's a compaction task that is running for the same time interval as that late event, Druid's locking mechanism that's based on time interval, it's going to essentially kill your auto compaction. And if this happens often enough, your compaction is never going to run. It's always going to get killed by those late events. And as I mentioned, yeah, this happens because of Druid's locking mechanism. So, just make sure that you configure that skip offset from latest to a value that where late events are not common. That way your compactions can finish. A caveat here, though, is that Druid actually released a new locking mechanism that's supposed to help a lot here. We haven't tested it in production yet, but we're really excited about it. And basically, the locking mechanism, instead of locking an entire time interval, it's going to lock segments. So compaction is going to be able to run even if you receive late events. And yeah, one last thing I wanted to mention with respect to compactions is that there's this configuration in Druid that basically will only run a compaction if the data that is trying to be compacted is smaller than a given value. And that's that input segment size bytes. So just make sure that's large enough to cover, if you're using daily segments, to cover the data that that segment might have in a day, the maximum segment size bytes. All right, so we've covered the streaming ingestion, how to optimize your data, and how to improve your data layout and segment pruning to make sure that your queries perform better. But I also mentioned that we do a different kind of ingestion, which is batch ingestion from S3. And we do this for two reasons. First is faster production rollout. So when we decide to add a new data type to Druid, we will actually publish the messages to S3 while we develop the pipeline, the Kafka pipeline to get data into Druid. And then when we're ready, we actually batch ingest that directly into Druid. And this makes us start the retentions of that data sooner so that we can get into production more quickly. But also disaster recovery. By having this data lake with raw events, we know that whatever happens in Kafka, in Druid, or even if we make a mistake in our enrichers that essentially enrich a property incorrectly and generate incorrect results, we can always recover from this raw data. So it's basically like an insurance for us. And the way it works is that we essentially have an S3 connector that it's continuously dumping data from Kafka into S3. And then there's a step 2 where we run Kubernetes jobs that are actually running the same code as our Kafka enrichers, and we'll receive that raw data and then publish it into another bucket, completely fully enriched and transformed. And really the only difference between this enricher and the one we use in Kafka is that in Kafka we read and write to Kafka, and here we read and write from S3. Yeah, and this is a very powerful, solution. By the way, one thing that I would recommend when you're ingesting from S3 is make sure that I would recommend using dynamic partitioning for your S3 tasks. And then later, once the data is in Druid, letting compactions actually apply the partitioning that you want. The reason is because if you ingest with dynamic partitioning, it's going to be a much faster. We measured the time that it takes for us to ingest completely a data source, the 3 months that we store. And actually, it takes about 2 hours for us to complete that. And that's because we first ingested a little bit unoptimized, and then auto compaction will actually clean it up. But, the problem with these batch ingestions is that they're very memory intensive. So how do you ensure that, if you're running something in the cluster, a workload that's very, very memory intensive and can potentially, kill a node, how do you ensure that your customers are not affected, and your ingestions are real-time ingestions are not affected? And for that, we use data tiering. So in Druid clusters, you can assign some data nodes to tier 1 and some others to tier 2. So what we do is tier 1 will actually hold all the data. It will run Kafka ingestions, and it will serve queries, of course. But our tier 2 is separate, and it only takes care of batch ingestion. So we can scale it out independently, run our 93 days batch ingestion, super memory intensive that may fail or may kill a node, and without worry, because tier 1 is already handling all the production use cases, all the customer use cases. So I highly recommend this. We use it in production, and the good thing about this is that you can dynamically change which tasks go to which tier by just dynamic configuration on the overlord, like the one we have here. And you can see, that Kafka is configured to go to the default worker category, which in this case is tier 1. And all our other tasks that are batch type go to tier 2. And you can change this at any time. So if at any point you were having problems with Kafka and you needed to scale up, you could potentially use tier 2 for Kafka if you wanted to, and then go back. There's no need to restart the cluster or anything. All right. I want to cover one other thing that is related to how do you handle schemas in Druid. You can imagine that we have 14 clusters, and we deploy the same schemas in each one of the clusters. So what happens when you need to make a change in your schema? You need to apply it to all the clusters. So you can quickly realize that becomes problematic. So we actually built a generic service that's based on Kubernetes Kustomize, if you're familiar with that, that basically keeps the common properties of data sources in a common folder, which we call bases here, and the overrides that need to happen in each environment in a clusters folder, such that if you need to define a different task slot for production or a different broker URL, you would define that and only that in the cluster section. And the dimensions and metrics, common things that are common to every cluster, go in bases. This way you can configure all your data sources, and if you need to make a common change, you just make it in bases and it gets synced to all your clusters. We're hoping to open source this at some point, but there's no ETA on that. And then the other thing that I wanted to cover is observability. How do you monitor your clusters? And for us, we really leverage our partnership with Imply. We use Implied Clarity, which is a great tool. You can visualize the performance of all your queries, the ingestions, and really navigating to how your cluster is doing. And also Pivot, which lets you inspect the data that you have ingested into Druid. Now, if you are not working with Imply, the other thing that we do use is Druid Exporter for essentially publishing metrics through Prometheus into Grafana. And it works well. It's just not that feature rich compared to Clarity. All right. So I've been talking a lot about our clusters and how we optimize performance, the different things and workloads that we run. I would like to spend some time talking about some of the challenges that we've seen with real-time ingestion. And particularly, I'm going to be talking about two of them. One is, how do you update data in real time? By the way, Druid does not allow this. And then deduplication is the other one. So yeah, let's start with updating data in real time. Druid, it's very powerful, and you can actually update data. You can, run a batch ingestion, and you can update, for instance, a full day of data. The problem with batch ingestions, though, is that there needs to be a delay until you can run it if you're running Kafka ingestions at the same time, and then it's memory intensive. You have to reingest a full day, for example, a full segment size. So really, the problem is that you can't do it in real time. You can't ingest one event and then modify it. So we just to describe what our problem was is, I mentioned we have agents, and these agents are sending metrics to Kafka and eventually to Druid, and they're continuously doing that. But we also have a way to determine if these agents are having problems. And if they are, we would like to mark the points that they send during the time that they had problems as, mark them as problematic points, let's say. So, the question is, how do you do this in Druid if you already ingested points? Ideally, you would want to come in and modify those events and mark them with a dimension that says, yes, they had problems, right? A 1 or a 0 or a true or false. They had problems. That way we can filter them out at query time. So really, how do you implement this in Druid? There's various ways you could go about this. One I mentioned already is batch ingestions. The other one could be, but the problem with batch ingestion is that it's not really real time. You have to wait at least, some period of time to be able to run the batch ingestion, and it's memory intensive. The other one would be at query time. One thing you can do is, you store all the state of which agents had problems at which time interval, and you save it to external system, maybe even Druid somewhere. And then you query that and use it as additional filters in your query, such that you can filter out the rows that had problems. The problem with this, though, is that it makes your queries inefficient, and also you cannot use rollups in your data, because once you roll up data, right, you may have combine, let's say, a few rows together, and if one of them had problems and some of them didn't, there's no way after rollup to filter out those that did have problems. So really, you can roll up your data. And the third way is one that we actually went with, and we designed it. And the way it works is that you basically ingest the data twice into Druid. The first time is real time, it goes straight into Druid. And the second one, you introduce a delay long enough to materialize all the state that you need for that extra enrichment. So in our case, if we detect local problems within 5 minutes, we basically delay our data, let's say 10 minutes to give some buffer. And then, you enrich it with all the state that has accumulated and ingest it back to Druid. So you have, two data sources when one is real time and the other one is delayed 10 minutes. And then what you do at query time is do a union query, kind of like this, a union query that queries both data sources, but applying a time filter where, the real-time data source, you only query the most recent 10 minutes. And for the delayed data source, you query data that is older than 10 minutes. So from the customer's perspective, they will see a complete timeline where the most recent 10 minutes are data as best that you could get it, but the data after 10 minutes, it's perfect. And well, this is how we implemented upsearch in Druid. And well, it's eventually consistent, let's say, at least. The other kind of challenge that we faced is with deduplication. And to be honest, duplicates don't have to be necessarily a problem, right? It really depends, and I kind of created this matrix to exemplify this. It really depends on whether you have duplicates in your pipeline, and what's your tolerance to those duplicates. Do you really care that they're there? And in some cases, you do care, because duplicates actually skew your aggregations. So you have a lot of duplicated numbers, your averages are going to skew towards that number. So, really, if you don't have a lot of duplicates, you may not care too much. If that's the case, there's things that you can do in Druid to fix this, or not to fix it, but to mitigate the problem with duplicates. And basically, it all comes down to doing rollups, using rollups to deduplicate points. So if you receive 2 events and they get rolled up together into a single row, you have effectively deduplicated the events. And you can do this at Kafka ingestion by setting the query granularity, the same granularity as the smallest time interval of your events. So like if your events are at most at 1 minute granularity, you want to set your query granularity to 1 minute, and then your Kafka ingestions will roll those up into a single row. But there are edge cases. What happens if one event reached one task, but another event reached another? If that happens, well, you'll essentially receive 2 rows, so they won't be deduplicated. Good news is, though, that if you had set up auto compaction with forced guaranteed rollup, after 1 or 2 days, whatever delay you put in your auto compactions, they'll get rolled up in that auto compaction, and after that point, you will have deduplicated data. So there are things you can do with Druid, but you can't 100% of the cases deduplicate the data in real time. So we actually had a case where we needed this, and I'm going to, well, essentially I thought I had another slide for this, but I don't. So I'm just going to explain it. There's, some of our agents for one of our product areas actually runs on laptops of employees. So, you can imagine that when you're running an agent in a laptop, you can lose connectivity for all sorts of reasons. The user may close the laptop, they may be in a coffee shop and they leave, or maybe, you lose Wi-Fi connection for some reason. So in those cases, our agents, if it's submitting a point and it doesn't receive an acknowledgement back, it's going to retry the next time that it's online. And therefore, you receive 2 events in the pipeline. And we were seeing this with one of our product areas where we were getting about 3% to 10% of duplicates. And the only way for us was to implement a deduper service that sits in front of Druid and deduplicates points. So it's something to watch out for. If duplicates are a problem for you, you may have to implement some service like this. And well, just to comment, I think I have a few minutes just to comment what our service was. We implemented a generic service based on Kafka streams and RocksDB that's integrated with Kafka streams. And the way it works is that you have to pass a Kafka header that contains the unique message ID. And then we essentially hash that ID and save it in RocksDB. And then, when a second points come in, we will query RocksDB to see if we already saw that point. And if we didn't, we'll let the message go through. If we did, then we essentially drop it. And there's a lot of optimization that RocksDB does for you to be able to support this very well. One of them is that it uses Bloom filters. That these are this in-memory data structures that can tell you with 100% certainty if some event was not in the set of events that we're seeing. And when you're working with duplicates, in the majority of cases, events are not going to be in the set that you already saw. If you have 3% to 10% of duplicates, you have 90% to 97% of not duplicates. So, in the majority of cases, you don't even have to read the database. You just let the message go through. So yeah, it was a really effective way of deduplicating data for us. All right, close with some conclusions, and then we'll get to questions. Druid was the right data store for us. We achieved a 10x latency reduction, but as always, consider all your use cases and have to make a technology choice that's the best for your use case. Then also, query performance. When you think about query performance optimization, make sure you think about data layout first. And dual ingestion for our case worked really well. We were using Kafka and also S3, which acts for us like an insurance. So I recommend it. And finally, make sure to watch out for real-time ingestion challenges, because they may be there. And that's it. Are there any questions? By the way, if you need to contact me about any further questions, this is my email.
Thank you, Gabriel. That was a fantastic session. I have a couple questions here in the chat room, and I'll just ask them. So could you tell me a bit more about your record counts in the 10 terabyte production data? This was from Prabhu.
Sorry, could you repeat the question? I couldn't hear very well.
Oh, my apologies. So basically, the record counts in 10 terabytes of production data. Could you use an approximate number of columns for the aggregations and the size of the Druid cluster, like the number of spec nodes? I'm reading off the chat room.
Yeah, so in terms of how many rows we ingest about 1.5 billion data points per day, and we store 3 months. So from there, you can kind of calculate how many rows we actually store, and sum up to 10 terabytes of data. So it's 1.5 billion times 90 days.
Cool. Prabhu, did that answer your question? And I think I asked, what is your enricher? This is my own personal question, by the way. Like, how are you enriching the data? Is it just Kafka streams, or do you have something else going on?
Yeah, well, we use different services. We do use Kafka streams, and we also use regular Kafka consumers and producers.
Cool.
We enrich with different, metadata from other sources within ThousandEyes, and also local problems, for instance. But yeah, we use different technologies, mostly Kafka streams and Kafka consumers and producers.
Wonderful, wonderful. Let's see, did another question come in? How many dimensions?
How many dimensions we typically store in our segments?
I guess, yeah.
Yeah, definitely. Well, let's say it depends on the data source, of course. For some we have more, for some we have less, but I would say anything between 7 to 15 dimensions per data source.
Cool.
And I think I see another one where we enable force rollup. If force rollup slows down the ingestion. The answer, yes, it is more memory intensive. It is more data intensive. The thing is, we can't really enable force guaranteed rollup on Kafka ingestion, so that always comes in with that set to false and a dynamic partitioning. But then our compactions are the ones that enable that force guaranteed rollup. And sure, it makes the the compaction tasks more intensive, but at the same time, because compaction tasks can fail and then they can be ran again, it doesn't really, it just takes longer to run, but not much longer. Maybe between 20 minutes to 45, and some more failed tasks, compaction tasks, something like that. But for us, it hasn't been a problem to run force guarantee rollup in production for compactions.
Questions. Oh yeah, how are you doing your schemas, the YAML files? Is that something you cooked yourself in YAML, or is it based on Avro? Like, what was your initial inspiration for that?
Yeah, so we actually use JSON as the data type to ingest into Druid. We looked into using protobufs because you use it in other places in ThousandEyes as well, but we didn't find that protobufs were very mature in Druid. Let's say it's just easier to ingest JSON because Druid speaks it completely. So really, for our project, we use YAML, and the YAML is translated into JSON. And then that JSON is what we pushed into Druid.
Okay, cool. At least in past projects, when I was a Kafka consultant, I would use like JSON schema. Some customers liked that, but YAML sounds like a pretty nifty approach as well. And I'm excited when you have the chance to open source it. The community would love to see more about it.
Yeah, hopefully soon.
From Jason Schmidt. With a RocksDB deduplication solution, is there a risk of dropped events, or do you end up with a guaranteed exactly once ingestion?
That's a great question. If you use Kafka streams and you enable exactly once, it actually configures exactly once in the RocksDB data store. So like if you write into RocksDB and then you can produce for some reason and the transaction gets rolled back, the item that was written to RocksDB gets unwritten, let's say. So it gets rolled back as well. So there's no risk of data loss there.
Yeah, when I was a Kafka consultant, the best way to do end-to-end transactions in Kafka was just streaming. So that's a pretty cool approach. Okay, we have another question from Jason Lee. Have you considered using Druid lookups instead of enriching the data? I think he's talking about the union queries. What are your thoughts on that?
Yes, we have. The problem with lookups is that if the state that you need to be enriching with is large enough, it needs to be stored in like every single machine. So you have to be very careful with the breadth of what you need to store there. We found that denormalizing your data, if you can, is better. The only reason we would use lookups is if the state on the rows changed over time. So like maybe you imagine, for instance, something called like labels. If you have labels that change over time and you want your results to use the latest state of those labels, then you may want to use lookups so that you can change the state in the lookup and that changes your aggregation. But for us, denormalizing the data was the way to go. It was more performant.
Well, I don't see any more questions. Guys, get in your questions if you have anything else to ask. Well, Gabriel, this was a lovely and highly engaging session. I personally learned a lot. I'm sure several other people in the audience did, along with Jason, and Prabhu and Sylvia. Thank you so much.